Okay, so thank you for the introduction, and thank you for giving me a chance to speak in this conference. I met Bjørn long ago. It was in Urbana-Champaign. It might have been a Midwest topology conference. Maybe not. Okay, but anyway, it was Urbana-Champaign for sure. And we were walking together with a group of people and talking about mathematics. And I thought Bjørn is a wonderful person to talk about mathematics with. And that turned out to be true. So I've used a lot of his work. I had the pleasure of writing 2 papers with him and with Birgit. I taught differential topology twice, once before Bjørn's book and once after. And everybody was happier the time I taught it with the book. And yeah, it's been great. So happy birthday in December and many, many more. Okay, so my subject is Loday constructions on spheres and tori. So actually, this is the non-equivariant work that Birgit was generalizing to the equivariant setting yesterday. So again, the idea is that, no, that's not this one. No, this one. Good morning. Yeah. Okay, so K is a commutative ring or ring spectrum. And A is a commutative K algebra. And in the discrete case, it sometimes also is a graded K algebra or a simplicial, always commutative K algebra. And so, yeah. And so the idea is that we have a functor from finite sets to K algebras, sending x to the tensor product over all x and x of A. And then if you have f from x to y, again, this was discussed yesterday, I'll just write it more explicitly. So it gives you f star from the tensor, from the tensor over x of A to the tensor over y of A, sending monomials to monomials like that, where by is the product over x in f inverse y of ax, and that's why we have units, and that's why we have commutativity. And we can extend, let's try to send this all the way down and this all the way up. Great. So we can extend to infinite sets by direct limits, and to simplicial sets by doing it level-wise. So basically, if you have an x, you're going to send it to the thing that sends in to the tensor xn, xn, a. And the simplicial structure maps go by that recipe there. And this thing is the thing we call Lx A. All tensor products are always over K. If we want to emphasize that, we can also write Lx K A. But basically, all tensor products are over K. And L is for the Loday construction. And there's some basic properties that are, 2 of them are very, very easy. So the first one is if you have a simplicial set X and subset Z, which is a simplicial subset of Y and X, you can glue X and Y along Z. And then you get that it's LXA tensor over LZA with LYA. And that's just done level-wise. I mean, if you're tensoring, you want one copy for each element in here. So you don't want the guys in Z to appear in two places, so you glue them. So that's a good property. The second one, which is less easy, but it says that if you realize LXA, the okay, I should have written, the homotopy type of LXA is it depends only on the homotopy type of X. And as Birgit said, it's even weaker. But if this way I can say it for spectra and discrete rings at the same time. And the easiest way to do it is EK, easiest reference, not the easiest way, but EKMM based on also older work of McClure, Schwenzel, and Vogt. So the point is that for spectra, LXA is the internal tensor of in the category of spectra of X with A. And so an invariant. And of course, this EKMM do it also over, not just over the sphere spectrum, but over other spectra. So you could just get the discrete case from it. In particular, if you look in the discrete, in particular for the discrete case, if you look at pi star of the realization of LXA, which in the discrete case is the homology of LXA with the alternating D equals sum. I goes from 0 to whatever, minus 1 to the I di. Depends only on the homotopy type of X. Okay.
Ayelet, may I ask one? I mean, you said it depends on less than somehow the Z homology type or something, right? What Birgit said, if I remember correctly. And why did you say this is different for spectra and like in algebra? Isn't it in both cases the same?
Oh, okay. Okay. I knew it to be true for the discrete case, and I did not assert that it was false in the spectrum case. So I'm happy it is, and I'm learning something. Thank you. Okay. So it depends only on the homotopy type of X. And the third thing, and this is another easy one like the first one. So if you take Lx of Ly of A, so we said that, and that we're also willing to consider it for simplicial gadgets, then that's exactly the same thing as, well, okay. This is bisimplicial. Okay, I'm gonna say what it is, and I'm not gonna make an appropriate sign. So what I'm really trying to say is this is a bisimplicial thing, this is a simplicial thing, and this is the diagonal of that. And so this is just, again, bookkeeping can be checked level-wise. What do we do here? For each n, we take the tensor product over elements of X of tensor product over elements of Y of copies of A. So that's the same thing as taking a tensor product of elements over Xn cross Yn of A at each simplicial level. So this is just the diagonal of that. Okay. So these are useful properties. And so there's a case that and it's been mentioned yesterday in at least 2 talks, the case we know. X is the smallest model of S1, 1 vertex, 1 edge. And of course, all these simplicial magic things, they require degeneracies. So with degeneracies, what does the simplicial model have? It has n plus 1 n simplices. So one of them is the degeneracy at the point, and then the other n are degeneracies over this thing, where you can take a bunch of vertices, send them here, and the rest send here. And of course, if you send all of them to the beginning or to the end, you don't know the difference. That's the one here. So you have n plus 1 things in dimension n, and boundary maps send things to neighbors, except for one weird one that sends something to the last one, because if you send one point to the beginning and all the rest to the end, and you get rid of the beginning, you send all your points to the end. So this is LS1 of A is the thing we call, well, I can call it the Hochschild complex of A, topological of A is a spectrum. Okay, so that's an example we like. Why do we want others? So there's 3 reasons, at least. One is for a commutative ring spectrum, we have the topological Dennis trace from Ka to THH of A. But then we get another commutative ring spectrum, so we can iterate, so we can map K of A into this thing is S1 of A. So we can iterate and map it into S1 of S1 of A, which by what I wrote there is L of S1 cross S1 of A. And of course, if you keep on doing it, you map in higher and higher tori. And there's the hope of learning, and there's work of Dundas and Carlson and Brunn on this. So there's hope that you can learn between the 2 trace redshift phenomena in both. This is a connection between the Loday construction of over tori and something we're interested in. And the second thing is study properties of ring spectra extensions. So the point here is that for discrete ring extensions, there's all these properties the extension could have, and those properties have implications for Hochschild homology. When you try to study extensions of ring spectra, it's a zoo, many more divergent kinds of behavior. But you can look at the behaviors on topological Hochschild homology and try to come up with adjectives you can put on extensions in an analogy to the discrete case. And this sounds like a good method, and it's been done. Like we've done all the Hochschild homology calculations we've done until now. That's a pretty nil statement. And we've gotten the distinctions that we've gotten from them. If we tinker with the invariants we're calculating, working no longer over circles but over other spheres, we'll get more behaviors that we can study. So that's another good motivation. And the third is we can stabilize S1 smash for any space, but in particular for spheres, LSN A into LSN plus 1A. And the limit is known to be interesting. No, it's been studied, gamma homology. Is that because I don't know how to calculate this in many cases, or well, whatever? A gamma homology in discrete cases, and TAQ for spectra. Okay, and it is a hard calculation, but it goes somewhere interesting. So after all this discussion, it seems like the place to begin would be spheres. So let's talk about higher spheres. No, this one, no. Okay, come on. Good. Okay, so spheres. So the good decomposition is Sn is dn joined along Sn minus 1 with dn. And therefore, you get that by my properties that LSN of A is LdN of A tensor over LS1 A L dn A. But if A is, for example, projective over K, then this guy is cofibrant over this. And on the other hand, dn is homotopy equivalent to a point. So you could say that LSN A is A, which is equivalent to this, derived tensor over LS1A with A. And that gives you a spectral sequence. Oh, sorry. One became, yeah, I'm sorry. N minus 1 became, N minus 1 became 1. That's bad. Good. So this gives you a spectral sequence, E2 star star equals tor star star of pi star of LSN minus 1 A and A, and it converges to pi star of LSN A, pi star plus star. And this is very useful. So, yeah. So, an important case is, for example, A equals HFP. And Hochschild told us that pi star of LS1 of HFP is isomorphic to FP U2. So we know it. And John Rogness started setting up the this kind of spectral sequence. And for example, in the case of 1 going on to 2, it has to collapse at E2. So this thing gives you this. And he kept on going for a while, and it had to collapse. And then Bjørn's student, Torleif Veen, he checked more and more structure, and he showed that this spectral sequence had to collapse for n less than or equal to 2p. And so maybe I should write some people's names. No? So Rogness. Okay. Yeah. Okay. This is a little complicated. Mike Mendel and Maria Bastera did something that they didn't publish, and we weren't aware of it. Who asked that? I'm looking at the... Okay. So the way I know the story is Mike and Maria Bastera did it early and didn't publish it, and we didn't know it. So we knew only about John Rogness, and then we knew about your student. Oh, doesn't your student thank Rogness in his thesis? Yeah, so that's how we know it. Okay. Okay. So collapse for small. Okay, and then it turned out Maria Bastera and Mike Mendel knew it in a totally different method. Earlier, I didn't know earlier than that, but earlier than what I'm going to write here. And when we just did it for all, and in a yet different way later, we mentioned them. Okay, this is the complete story as I know it, and some things I can't relate, I agree. Collapse for small n, and Wien for n less than or equal to 2p by studying more structures. That just it had to collapse. There are no differentials, so it could be non-zero. And then with Bobkova and Poirier and Zakharevich, we did it for n less than or equal to 2p plus 2 by studying more structures, and there just couldn't be differentials. But then in 2p plus 3, there was a differential that no hop algebra, careful bookkeeping could outrule. There was a differential that really could be 0 or could be not 0, and we didn't know what to do at the time because we weren't aware of the work of Maria and Mike. Okay. Okay. But there were discrete cases where we had collapse of the spectral sequence forever. And that was also with these people. And again, whenever I write people, it's always with Birgit. Every single thing I talk about is with Birgit. And they were, so K, a characteristic P field. So you could look at K, X, and I'm allowing now to have graded rings. So this guy can have even degree. And I can take exterior over K of X, and it had odd degree. And I can look at Kx modulo X to some power divisible by P. It doesn't have to be, this P times M doesn't have to be power. And this guy, again, has even degree. And if you want one level of collapse, in fact, you don't even need fields, and this could be just a ring, and here it could be a ring where P equals 0. Okay, so you have all these cases. So let's see what happens in these cases. No, it is coming down. That's nice. No, keep on coming. What's special about these cases. And it is that the Hochschild complex of A is a chain homotopy equivalent to its homology as a formal complex sitting inside it. In a multiplicative way. So in these cases, the homology is the homology of a formal complex that sits inside the Hochschild complex. And what happens is that the map that sends basically a thing to its homology class is not surprisingly multiplicative. And therefore, to calculate let's talk about derived tensor over LS1 A, I can look at the double complex bar A, the Hochschild complex of A, which is a good way to approach this, but I can go and replace this by the formal complex and go from this double complex to another double complex that's going to have the same homology. But if I replace the columns that have the Hochschild homology A by the formal columns, I'm basically taking a double complex and saying that its homology is going to be the same as the homology of a double complex where all the downward differentials are 0. So that collapses at E2. So a double complex with 0 vertical maps, and I get that LS2 of A is just isomorphic to Tor of L. Pi star of LS1 A. And not only that, but these Hochschild homology groups that sit inside as a complex, so they are basically, oh, and I'm working over a field, by the way. So if I'm so good in dealing with rings of these 3 types that I wrote, I'm also good at dealing with tensors of rings of these types that I wrote. And moreover, the Hochschild homology of A, for A equals kx. So again, k is a field of characteristic p. I get fpx tensor exterior over k epsilon x. Epsilon x, remember this was even degree. Epsilon x is degree 1 more, so it has odd degree. And A equals exterior kx. I get exterior kx tensor divided power on rho 0x. Now, x was here odd degree. Rho 0 is degree 1 bigger than degree of x, so it's even. And fp x over xpm has a Hochschild homology, A equals this. Then I get fp x over xpm tensor an exterior on an epsilon x, which again is of odd degree because the degree is 1 greater than the degree of x, which was even. Tensor an exterior over rho 0 epsilon x. And this increases degree by 1. This increases degree by 1. All in all, I added 2 to the degree I started with even. I'm back in even. You might complain, I didn't say anything about divided powers. But my characteristic is p. So my divided power just splits as a tensor product of polynomial things over pth power gets identified to 0. So in these cases, I had good rings to begin with, which gave me one step. But then I ended up getting things that were good for me too. And I can keep on going forever. It gets bigger and bigger, but it works. So I get collapse forever. Meaning that the Loday constructions over spheres, which could be regarded as iterated topological torus, are in fact iterated algebraic torus, and the iterated algebraic torus are cumbersome, but we have formulas for them all the way. Okay, so that was good for the algebra case, and so what happens in the HFP case? And that is where Bjørn comes in, and where we found out that Mike and Maria had done it before.
But maybe I missed some points. I mean, you somehow this vector sequence, but it seems to me that you said that there's no extension problem.
Oh, I'm working over a field.
But even for fields, I mean, you identify them as groups is okay, but if you're multiplicative structure.
Oh, okay. So I guess what I would. It's okay. I mean, I guess the reason I would say is that the product, you can check directly. I can't think of a better general reason, but it does work. You can check directly.
Okay, and I have another question. So here you somehow have a decolage because you somehow move that exterior powers to divided powers, but how you go further? I mean, it seems to me that you iterate this procedure. You need to do something like a divided power, then you still decolage, but this thing is not concentrated in some degree.
No, I mean, it keeps on going. You do the procedure, you do the Tor procedure to each of these, and then each of these splits as 2 of these, and each of these splits as these. It just keeps on going like that. Basically, when you take the Tor over a tensor product of 2 things, of A with A, it splits as the Tor of each of the things of A with A. And so you could just break down the calculation and keep going. But your algebra structure point is well taken, except it's okay because if you look at the generators, it is okay. But okay, so how about HFP still? So this is also joined with Bjørn. So. Well, okay, so we know that THH star HFP is isomorphic to FP of U2. And by all this recipes, pi star of LS2 HFP is isomorphic to the exterior over FP of some I'll call it V3, whatever you want to call it. Okay. And then Mike Mandel said if you have a commutative augmented HFP algebra with this homotopy, there's a chain. There's a chain of weak equivalences from that to HFP join sigma 3 HFP with a square 0 operation. So this definitely satisfies these properties, but up to weak equivalences back and forth, it's the only one. So we know, so we understand this up to weak equivalence. And then we can consider the image under the Eilenberg-MacLane functor of the simplicial commutative HFP, simplicial commutative FP algebra that just takes the free FP thing over delta 3 modulo its boundary. Okay, and it's going to also be a commutative augmented HFP algebra with homotopy this. So it's also equivalent to that. Okay, and then we can look at this simplicial algebra, and we can normalize this. But let's normalize this simplicial guy, and we just get the okay, I guess FP semi-direct sigma 3 FP as a graded algebra. So there's this chain of things. And for each of them, you could do Loday constructions and see what you get. And for this one, this is a strange way of writing the graded ring that's the exterior over FP over a generator in dimension 3. So for this one, the spectral sequence that we're always looking at, it collapses, in fact, forever. And then you can set up analogous spectral sequences for this and for its Eilenberg-MacLane version. And you get isomorphic spectral sequences. So if this guy collapses because it's one of the cases we like, then the one for this one collapses and the one for this one collapses. So suddenly, HFP went on this category, on this bunch of discrete cases that we liked. It took a ride on them, and it got to collapse as well. So we get that pi of LSN of HFP is isomorphic to tor of pi of LSN minus 1 HFP of FP for all n. Now that by the time we submitted the paper, we for sure knew, even I knew, that Mike and Maria had done this years earlier. So that wasn't our main result. What our main result was that, well, you can also take, if you have pointed spaces. So I'm taking a tensor over any element in X of A. If I take an A module and I put it on the base point, and then everybody can multiply into the base point, because the base point doesn't go anywhere, I can also do this thing with coefficients. So with Bjørn, we also calculated that pi of LSN HZ HFP is isomorphic to tor pi of LSN minus 1 HZ HFP HFP sorry FP FP for all n, and that was a new thing. It was a slightly more complicated construction, so that's why I'm not discussing it, but that's what the method got us. And we even looked at rings of integers and finite extensions of QP. And again, we could do the ring of integers with coefficients in the quotient of the ring of integers by a prime ideal. The reducing the coefficient somehow gets you into the field case, and a lot of things, like all this breaking up of tensors and all that, the field case is really good. Actually, in a later paper with Bjørn, we showed that.
I'm getting confused. So here you have coefficients. So,
yeah.
So the Loday construction will give you something like I mean, it's not from the category finite, but somehow
Pointed.
pointed finite.
Yeah, exactly.
But Sn, how you point it?
Well, I take it, S0, I take one of the points, and that's the base point, and then S1 is built on the basis of that, and that point remains. So I just start with the base point in the beginning, and then I keep on including S1 into S2, and S2 into S3, and I keep the base point that I had from S0.
Enjoy another point.
No, it's one of the 2 points of S0. Yeah, and then also with Bjørn, we calculated pi star of L S2 HZ without coefficients. But that was getting complicated. So this was just like analyzing the torsion step by step. Whatever. That's how we got the discrete case to help us with HFP in one case. And HZ. Because. OK. And now I want to move on to Loday constructions on tori. So, weird fact. For some K algebras A's, if the suspension of a simplicial set X is equivalent to the suspension of a simplicial set Y, and I really mean this in the weakest sense, like not even that there's a map from F to Y that isn't an isomorphism, isn't an equivalence unto a suspension. Just if this is true, then pi of Lxa is isomorphic to pi Ly. So of course, by what we said, if the suspensions are equivalent, then the Loday constructions over the suspensions will be equivalent. But there's no particular reason to say this. And can't expect this. And we call it stability of A over K. And of course, for any xy, then if I look at the suspension of x cross y, that's equivalent to the suspension of x and the suspension of y and the suspension of x smash y. And if I have L V join W A, that's just L V A tensor over A L W A. That was my formula of joining two x and y along Z in the beginning. So I'm just joining V and W along a point. The Loday construction on a point is just A. So I know this. So I get that if A is stable over K, then if I wanted to do the Loday construction, of, for example, of S1 cross S1 of A, that's isomorphic, that's equivalent to the Loday construction of S1 A tensor L S1 A tensor L S2 A. And if I keep on going, then I get that L T N A is equivalent to the wedge, to the tensor over A. K goes from 1 to N, a tensor over N choose K. That's the number of, so I mean, if I can decompose in this way and take threefold product of S1s or fourfold, and then the question is how many simplices in each dimension I will how many spheres in each dimension I will get if I want to have something that suspends to the same thing as a torus. And the answer is n choose k of dimension k, L, S, K, A. This is also over A. So if you have stability and you know Loday constructions on spheres, then you know Loday constructions on tori. And, OK. So what is stable? And Dundas and Tenty said that if you take free symmetric K algebras over some simplicial W, so you'd write that EKW. So you take the free K thing over the infinite symmetric thing over W. These guys are symmetric over K. In the zero-dimensional case, so certainly K with a variable or K with a bunch of commuting variables, these are stable over K. And the idea there is if you do L over X of EKW, well, that's the same as doing L over W of EKX. And EKX could be regarded as the free K algebra on the infinite symmetric thing on X, which depends only on the suspension of X. So if you know the suspension of X, you're going to get the same thing. So that's good. In the spectrum case, we're able to generalize this. So you can take M a K module. So K now is a commutative ring spectrum. And you can look at PKM, which is just n greater than 0, m n over sigma n. And this is stable. Again, this is the analog of the free thing. Here it's free over a module. So this is stable over K. This is even easier to see because if you do LXK of PKM, you can show that it's equivalent to PK of X smash X plus smash M. So again, you move it to the stable world. So it's determined by the suspension of X. So, so that's good. And then we can do localizations, extensions of these. So in the discrete case, that's how Dundas and Tenty get all smooth algebras. So you can do stuff. Another result is okay. Another result is commutative Hopf algebras. So that's a little restrictive. Over K are stable over K. So this is actually a result of Berest, Ramados, and Young. And the idea there is, in general, the commutative algebra maps from LXH. So H is the commutative Hopf algebras H. So, and some other algebra B is in correspondence with the top maps from X to map HB, which, if I want, could be top pointed maps from X plus to map HB. Okay, so far we didn't use the fact that H is a Hopf algebra, but if H is a Hopf algebra, this has an E1 product. And so the maps from this guy to this E1 space are in correspondence with maps from the free E1 space on this to here, which is loop suspension X plus into this monstrosity. But again, this only depends on X plus, so it's stable. But of course, it's a very restrictive condition that it's a commutative Hopf algebra. And with Klanderman, Hedenlund, and Zhu, we were able to generalize this to commutative Hopf algebras in spectra. So that was a good case. And here's some more good cases. If we take the Loday construction over suspension, this is stable over A. And other cases. If R is commutative and A in R is regular, then R mod A is stable over R. Also, if A1 through AM is a regular sequence, you get that R mod, the ideal generated by them, is stable over R. And also, one more stability result. If you look at the square zero extension HR over A, joint suspension of HR over A is stable over HR over A. So that's a list. It doesn't look like I'm going to cover all the rings in the world, and I'm not going to, because Bjørn and Andres Tenti, they showed that you don't need to go very far to find a non-stable example, namely Q T modulo T squared is not stable over Q. And by the way, this shows that stability is not transitive. Because if you look at QT, it's stable over Q because it's free. That's the first case we were talking about. And if you look at QT over T squared, I mean, in QT there are no zero divisors. T squared is a perfectly regular element. So that's stable over QT. Okay, but out of luck, you don't have transitivity. With these people, Klanderman, Hedlund, and Zhu, we generalized the Dundas-Tenty example to show that QT modulo Tn is not stable over Q for all n greater than 1. And one thing that's interesting is that Dundas and Tenty caught Qt mod T squared for being bad, for being not stable, over the 2 torus. And when we looked at these guys, we caught each of these as not being stable over the n torus, Tn. Now, we haven't proved that you couldn't do some smaller thing, but that's where we caught it. And yeah, and that's basically what I wanted to say. We were hoping for some miracle that would, again, get us from discrete cases we could do for to HFP. So I should write also that Bjørn's student Vane that we talked about in the beginning, he showed that HFP behaves stably on Tn for all n less than or equal to p. But somehow we haven't found the trick to move us from discrete world to spectral world. So we wonder if HFP is stable over S. I would really like to know that. But that's what I wanted to say. Thank you.
Are there any questions?
Yeah.
So by commutative Hopf algebras and spectra, is it like strict, or is it some more flexible,
It's
infinity-ish kind of
it's
instance?
it's strict.
Okay, so
It's not, yeah.
so like over the sphere spectrum, there's not many of them. Okay.
And even for discrete rings, commutative Hopf. No, I mean, it's really not. I mean, it clearly. Well, I mean, you look at their counterexample, right? It's clearly not the trend that's going to sweep the nation. But it's just weird that it ever happens. But yeah.
Shouldn't it be true for weak? I mean, like actual infinity Hopf algebras as well.
Yeah, I mean, the proof that's sort of written down for algebra, if you translate it, then you better work with infinite families.
Oh, so we do it for? Okay, sorry. So, okay. So, but still there aren't that many. It's, yeah.
I have a question kind of related to both your inverters talk. I was wondering if you thought about the equivariant analog of these stable phenomena.
So that's like doing it for Loday, for Tamara functors. So
Yeah,
so that's what we're. So that's what.
Specifically about stability?
Oh, stability. No. I mean, in a way, the reason is that we have been doing baby calculations and we're not quite there yet. Is there a reason that that you would be particularly useful for something?
Just curiosity. I mean, because you could stabilize with respect to
Oh.
Rho.
I see. Okay, so that's interesting. Unfortunately, with the Tambera functors, we're really just beginning to come up with examples. But okay, but I'm registering that we can have a whole family of this property. And yes.
Are there more questions?